Hello, and welcome to Empowered Learning. This video will be about linear programming models, and in particular using the Microsoft Excel solver feature to be able to find optimum solutions for linear programming model problems. And we'll see various manufacturing examples to where we are going to analyze a situation. We're going to take that situation and translate it mathematically, see how we enter it into Microsoft Excel, and then run the Excel solver to get these solutions or the optimum solution. So we're going to start with this first example here, and this is an example to where we have a furniture company that's making tables and chairs, and we have some constraints on the amount of labor hours that the company can pay its workers for a particular production cycle, as far as making the chairs and painting them. We also have some constraints from the marketing department as to how many tables and chairs to produce, and we're also given information about how much profit we expect to get from each table and chair. And then using all those constraints, we want to come up with a optimum solution that will allow us to be able to maximize our profits. So in essence, this is what this example is about. So it says the Flair Furniture Company produces tables and chairs. Each table takes 3 hours of carpentry work to create and 2 hours to paint. We also see that each chair takes 4 hours of carpentry work and 1 hour of painting. And we are maximized to 2,400 hours of carpentry work, and that just means that we are actually assembling the chair. And it takes 1,000 hours, that's the max that we have to be able to dedicate towards paying workers to paint these tables and chairs. And our marketing department wants to limit the number of chairs to be produced to 250, meaning we have, not 250, 450. So that's going to be 450 chairs or less. But we want to sell at least or produce at least 100 tables. And then each profit, the profit for each table is going to be $7. Profit for each chair is going to be $5. So we have all that information. Now, if we are going to put all this together, this is what those constraints look like. And so for the profit equation here, this is what's called our objective function. And of course, the objective is to max profit out. So we also see that we want to max out profit according to these constraints. And so this is the constraint about the carpentry work. This is the constraint about the painting time, or painting work. And this is the limit on chairs. And this is the, I guess we'll say limit, but it's really a minimum on tables. Now, what I want to focus on is mainly these four. And so if we look back, we see that they gave us information about tables. So I'm going to put everything that has something to do with tables in, I'm going to underline it with blue, and then everything else that has something to do with chairs, I'm going to put that in red. So here it says each table takes 3 hours of carpentry work and 2 hours of painting. So that's for the table. We also see that for the tables, we have at least 100 tables produced. So we have that information as well. So here we see that if we're looking at this, we have for carpentry work and for painting, we know that there's going to be 3 hours for a table, and it's going to be 2 hours um, of painting for it. Okay, so 3 hours of carpentry work, 2 hours of painting. We also know for each chair, and so I'll go ahead and put this in red. So for each chair here again, it's going to take 4 hours of carpentry work and 1 hour of painting. So here that would be 4 hours of carpentry work, 1 hour of painting. And we see from there, we know that the maximum amount of carpentry work that we can pay for, regardless whether it's for tables or chairs, is going to be 2,400 hours. And for the painting, it's going to be 1,000 hours. So in knowing that, we know if we add the amount of carpentry hours and for the tables and the chairs, we know that that's going to max out at 2,400 hours. And if we add the amount of painting hours for tables and chairs, that's going to max out to 1,000 hours. And we know that if we can't do more than 2,400 hours here, then that's why we're putting the less than or equal to sign. And of course, if we can't do more than 1,000, then we're putting the less than or equal to sign there. And of course, that just less than or equal to means that amount or less. So this is how we actually come up with these two inequality constraints. So if we go back, we see here that for the tables, it says at least 100 tables. And we also have information that it says it limits the number of chairs to be produced to 450. So that means no more than 450 chairs. So as we were doing before, I'll go ahead and underline the limit of chairs to be at least 450. So that tells me chairs have to be less than or equal to 450. And we know that for the tables produced, they're going to be at least 100, which means 100 or more. So we'll just go ahead and put this down here. And so now you see how we get the C is less than or equal to 450 and T is greater than or equal to 100. So that's what we have here. These last two are basically saying that for this problem, it does not make sense to produce a negative number of tables or a negative number of chairs. And so as we go through the whole process of setting up this problem in the Excel solver, we will see where we actually have to go to make sure that our solutions are non-negative. And that's essentially what this says here. We want non-negative solutions because it doesn't make any sense to count negative tables or negative chairs. All right, so moving on here, this is one way that you can set up this linear programming problem. And of course, if you see the link here for the course that I'm actually doing this for, you could go here and you can download all the spreadsheets. For those of you that aren't in my course, you can download this spreadsheet here and, well, these spreadsheets rather, and you'll see this particular setup there. And I think it's a good idea to do that just to make sure that you're not sort of recreating the wheel for whatever it is that you may be using this for. You can sort of re-engineer the examples and the labels to sort of fit your situation. But it's good to start off with these examples here. So if we set this up, we see that we have our carpentry hours, painting hours, maximum number of chairs, that constraint, and the minimum number. And again, to make sure that our answers are non-negative, when we actually go into the Excel solver feature, we will address that at that time. All right, so we know what all of our constraints are now. And if we actually plug everything in, this is what it would look like, okay? And let's move forward here. So this is what you would actually be entering in as far as the, I guess the formulas are concerned. And if you notice here, you see that you have this function called sum product. And so what sum product is doing, it's taking two different array of cells and they're multiplying them together and adding the sum. So for example, here we know that these yellow cells here are what is going to be the cells that represent our decision variables, meaning the number of tables, the number of chairs. And this sum product function here is saying that we want every cell from B6 to C6 to be multiplied with the cells B5 to C5. So this is B6, this is C6. So we're saying, let's go here, multiply this cell times that cell, multiply this cell times that cell. And then we want to add the results of the product of B6 and B5 and C6 and C5. Now, for some of you that may not be too familiar with Excel, one of the things that you notice different here about this particular function in its syntax is that you'll notice that the B6 to C6 there has that colon in it, and that just means we want all the cells that go from B6 to C6. So we're talking about this cell and this cell. So if we were dragging going horizontally, we want to include all those cells. Now, the other thing I want to mention is, do you see how we have these dollar signs here? And so anytime we have a dollar sign on either a column or a row, then what that's telling Microsoft Excel to do is to hold that particular column or row. And so by having the dollar signs on both the column and the row, what it is saying is, regardless of what cells I have here, what I want to do is I want to make sure that they're always being multiplied times these two cells right here. So we want to make sure that they're always being multiplied by that. Now, to make my point, let's say, just hypothetically speaking here, and because this is actually what we do, we wanted to copy and paste, okay? So let's say if I wanted to do the carpentry hours, which is right here. So we know that when we do this sum product for this one, this is going to be 3 times whatever's in this column plus 4 times whatever's in this column. And so that's exactly what the B8 to C8 is doing. And then you notice that for all of these, they're referring to B5 and C5. By having those dollar signs there, it's preventing us whenever we, let's say we copy and paste and say, all right, well, I want the same kind of thing that goes on in the carpentry hours to go here. And normally in Excel, you would just copy and paste this and move it down. If we did that and these did not have the dollar signs on it, what would happen is let's say we copy and paste here, instead of this actually saying B5 to C5, what it would say is B6 to C6. And so instead of multiplying the 2 times the cell B5 and 2 times the cell B6, what would actually be happening here is I would be taking this cell here and I would be multiplying it times the 7 in this cell, which is B6. And I would be taking the cell that's here in C 9 and multiplying it, oops, sorry, taking the cell in C9 and multiplying it times this cell here in C6. So in other words, everything would drop down, okay? So to make sure that you see this in action here, I'm going to temporarily pause the presentation and actually pull up just a blank worksheet so that you can see this happen. And again, I'm only doing this for those of you who are not that familiar with Microsoft Excel so that you can see what these differences are. For those of you that are, you can just kind of move forward to me starting this presentation again. All right, so as an example here, I'm going to, I've prepared a little something here so that you can kind of see the difference in between whenever you have the dollar signs and when you don't. In this instance, I have two columns here, X and Y. I've pretty much made the cells that are highlighted here in yellow. These are the cells that I want to multiply everything with. So make this a little bigger as well so that you all can see it. So here, when I do the sum product with the dollar signs on these cells here, then you kind of see what the formula looks like. And basically all I did here, and I'll erase this so that you can actually see what I did there, is I actually came here and typed this in as you see it, and then I'm just going to copy and paste. And you'll see that when I do the copy paste, that these cells are going to change in the first array, but the second one is not. Okay. But here for this one, you see that I don't have the dollar signs on the cells A2 and B2. And so as I go down, you can see how everything is changing. And so that's how the dollar signs affect everything. If you're interested in knowing what the formulas look like, you can always just go to formulas here and go to show and then show formulas. And so again, I am working with Microsoft Excel for Mac users, 2011. Your view may be a little different depending upon if you have a newer version of Microsoft Excel for Mac, or if you are working on an IBM /PC type of computer. It may look different, but you can just easily Google it and they'll tell you for whatever type of version of Excel you have how to see this. So now there's some other hotkey ways to do it too. I just don't remember them at the moment. But as you can see here, when I copy and paste all of these dollar signs on the column as well as the row is basically holding these cells here whenever I do the sum product. Whereas over here, you see that everything is changing. And you see here, I went from A3, B3 to A4, B4, and this went down from A2, B2 to A3, B3. And so that's how the whole sum product works. So now we'll get back to the presentation. All right, so now you kind of see how this whole sum product thing works. So what I'm going to do now is kind of erase all this business here, and we'll go ahead and move on to the next slide. All right, so again, now you see how we actually have the sum product here. And so what we're going to talk about next is how we get all these coefficients here, as well as what we call these right-hand side coefficients. So if you see here, our profit function was 7t plus 5c. And all we're doing is putting the coefficients for the profit function here in these cells. And remember that this is 7 times t plus 5 times c. And that's how we get that. And sum product for this is going to be in cell D6. So of course, B6 and C6 are the coefficients. B5 and C5 are the number of tables and the number of chairs, which is basically our decision variables. If you see here, we have the 3 and the 4 from this constraint. The carpentry work constraint goes here. And what this is doing is actually calculating how many hours that we are actually using at the company. And so this is 3 times the number of carpentry hours. So 3 times the number of, 3 times the number of hours that we use to make the tables, carpentry hours, and 4 times the number of hours that we spend for the chairs there. And so for carpentry hours. And so we're just taking a total of all of that. And we see that here we put the actual constraint on the right-hand side. And so we call that a right-hand side constraint. So similarly for the painting, you see that coefficient of 2 and 1 there. This is actually calculating how much of those painting hours we're using. And we see that we have a max of 1,000. Okay. These less than or equal to signs here and this greater than or equal to sign, we're just putting that there for us in the model. But in all actuality, whenever we go to the Excel solver, we are going to actually tell the Excel solver which one to use. But we're just doing that for us so that we can understand our model here. If you see for the maximum number of chairs, you'll see that we have this, and of course there's an understood 1 that's right there. We do not, for the chair constraint, we do not have anything about tables, so that's why you don't see anything here. And of course we just put a 1 here for the chairs, and so 1 times anything is just that anything. So that would just be chairs is less than or equal to 450. And again, we're taking a tally on how many actual chairs we have, less than or equal to 450. And then for the minimum number of tables, same thing here. Understood 1, so we put a 1 here and nothing here. And when we put nothing there, it acts like a 0. So if you want to put the actual number 0 there, that will be fine too. And then again, here we have the greater than or equal to sign just for us, and we put the 100 there for the right-hand side constraint. And so now what we need to do to actually run the solver is we need to go to the data area. And so if you go to the data area, you should see solver here. If you don't see that, then you want to go to tools and then add-ins, and then you should see some kind of selection menu where you can select this particular file, solver.xlin. If you do not see that, then what you want to do is figure out whatever version of Microsoft Excel you have, and I would suggest that you YouTube it to see how do you add the Excel solver for your particular version of Microsoft Excel. If you're taking my course, then under the learning assignments area, you already have those links available to you. You can just go there and pick which one, watch it, and then set it up. So I'm not going to spend a whole bunch of time on that because you can research that part on your own, given that you find the links. But what I am going to do is run through how this is actually going to look inside of Microsoft Excel once you get that set up, so that you can see how to properly set up the solver. And so I'll switch from the presentation now to that example in Microsoft Excel so that you can see how we go through it from start to finish. All right, so we have the Microsoft Excel example here up in one of my worksheets. And so what I wanted to go through is go through the Excel solver, how we actually get to that. So let's just say we start here at home. If you see here, I have the data tab here. It may look a little different on your version of Excel, but you essentially go to data, and then within there under analysis, you'll see that you have the Excel solved. And so if you don't see this, then again, you need to go to your tools area and then go to add-ins and see if you see it there. Of course, for me, just so that you'll know what that looks like, I'm going to go up. You can't see this, but I'm going to go up to my toolbar here, and then I'm going to go to add-ins. And so you actually see the add-ins part there. And of course, this is what it looks like for me. And it'll have the solver.xlam there. If you don't see that at all, then one of the things you may want to do is download solver.xlam. If you go to that link that I gave you earlier about from the textbook that I'm using, then they have that information there as well. All right, so here we want to go to data, and then of course under analysis, hit solver. And so here's where we're going to put our information in. So we start off by saying we want to set the objective. Remember, our objective is to maximize profit. And so the cell D6 here is how we're calculating our profit. And so we're doing the sum of $7 times the number of tables plus $5 times the number of chairs, and that total is here. So if you notice, our objective function is going to be maxed out, so we'll put it there. If we were doing minimum, so like a minimum cost, we would do this. If we wanted to do, let's say, a break-even analysis, then we would want to click this and then say value of 0. Of course, if we're talking about profit, we know that break-even points happen whenever profit equals 0. So here, to get what we need in this cell here, we need to refer to cell D6. So let's go back to max, and then we need to click on this here, and then what this is doing is searching for whatever cell I want to use. So what I'm going to do is go here, select D6, and then you see how it says Flair Furniture example D6, and with the dollar signs on it, because I just want that cell. The Flair Furniture example thing just refers to what I have this tab named, or this worksheet named. And then after that, I click on this icon here, and you see that it pops up. And so I want to basically look at cell D6, and I want to maximize that by changing the following cells. And of course, what's in yellow is what I want to change. So I'll come here again, click, and I click and drag till I get all the cells I need. And you see how it automatically put the dollar signs on it. And click that icon again, and I have that in there. Okay. So that takes care of the actual profit cell, as well as me maximizing and the decision variables. So if we look here, we need the constraints now. And if you notice, this was the 3T plus 4C is less than or equal to 2,400 hours. So what we're going to do is put that in now. We're also going to put in the painting hours and the maximum number of chairs simultaneously. Because if you see, all these have less than or equal to in their inequality. So I'm going to add, and then after that, I'm going to pick the cell reference on the left. So I'm going to come here, and I'm going to talk about, no, sorry, that's the wrong cell. Let me clear that out. Clicked on the wrong thing there. So here, what I want to do is click on the blue cell here, because I'm actually calculating the carpentry hours there. So I'm going to go to add, click on this, and then click on this cell, and then I'm going to drag down to get the first 3, because all these have less than or equal to. And then I have that. Here we see that we need to pick either less than or equal to, greater than or equal to, integer, binary, difference. And so for this one, we just want the less than or equal to, so we'll keep it the same. And then we will come here, click, and then we'll do the 2,400,000 and 450 all together. And then from there we click OK, and now we have that constraint there for all of our less than or equal to inequality statements. So now we want to get the one for the greater than or equal to. So now we go to add again, click on this for the cell, and of course we'll go here. And now we switch this to greater than or equal to, and then come from constraint, click here, click on the icon, and then do OK. And so now we have all of our constraints in. This is check marked because we want to make sure that our decision variables, tables and chairs, or T and C, is non-negative. So this refers to the T being greater than or equal to 0 and C being greater than or equal to 0. So we want to make sure that that's checked. Whenever we're doing linear programming models, we want to do this in the simplex LP mode. So we want to keep this the way that it is. And for most instances here, as far as options are concerned, that just kind of deals with the run times and all that. You really don't want to mess with that unless you're really advanced. And so for what we'll be doing here in this presentation, we won't need to worry about that. So I'm not going to address that. So now that we have all this information in, we just click solve, and we should get an answer here in a second. So we see here that Excel Solver was actually able to find a solution. We see here that we can also print out some extra reports. And so in the presentations that we have ahead, we're going to actually look at some of these reports and be able to get a little bit more from our model from it. But for right now, we're just going to worry about the fact of we have an answer. And so we see here that in order to maximize profits with our current constraints, we would have to make 320 tables, 360 chairs, and the maximum amount of profit we would be able to get is $4,040. And so this is essentially how it works. So the hardest part for this, again, is to actually model a situation mathematically. And then after that, and it's once you're able to set it up, put it into Excel, the Excel solver part is relatively easy, like you see. All right, so we'll break away from this and we'll go to the next example, but I'll be coming back to this particular presentation here just so that you can kind of see how this works in real time. All right, so now that you've seen that, then these next few slides here just sort of describe everything that I was talking about. So we'll just go ahead and skip these. And so we see that we came up with this result here. All right, so now for our next example. So for this example, what we're doing is modeling a situation where we have a subcontractor that is going to produce ties for a high-end clothing retailer. And what's happening here is that we know that they want to make 4 different types of ties. So they have all silk tie, it's going to be all polyester tie, and then they're going to do 2 polyester cotton blends as far as ties are concerned. And what we see down here is just what we have per production cycle. In this case, it's going to be a month, as far as the cost per yard of each of the types of materials that we're going to use, as well as the availability of supply that we have and the maximum of that. So we have, says Fifth Avenue Industries, manufacturer of menswear, produces 4 ties. Of course, we went through the all silk, all polyester, and then we got 2 blends of polyester and cotton. And we know here that these are our cost per yard, as well as how much we actually have per month. So we know that the firm has fixed contracts with several major department store chains to supply ties each month. And the contracts require that Fifth Avenue Industries supplies a minimum quantity of ties but allow for a large demand if Fifth Avenue chooses to meet that demand. Okay. And it says here that most of the ties are not shipped with the name Fifth Avenue on their label, incidentally, but with private stock labels supplied by the store. So to give you an idea of what's going on here, let's say you go to a high-end retailer and you notice that they have ties, name brand ties, and then you have these other brands that you may not have seen before, but they look comparable to some of the other name brand ties that you see there. Well, what's happening is that that particular retailer is actually competing with the other name brand ties in this example um, because they want your business. Of course, they'll sell the high end or the name brand ties to get you in there, but they're going to say, hey, you can buy ours for a better deal. And since they're actually supplying it, then of course they can charge a little cheaper than what the name brands would charge. And so the subcontractor that makes these ties, they're saying, hey, we have a direct relationship with them, so we can kind of cut the cost a bit, but we want to make sure that we have a minimum amount that comes to our storage each month. And so the men's clothing retailer would basically set that number in the negotiations. They'll say, all right, well, we got to have at least this much. The actual subcontractor, that's actually going to produce the ties, they're going to worry about the number that's on the high end, saying, hey, we don't want to produce any more than this. And of course, you can understand why. If we have a situation where, let's say, the subcontractor produces 10,000 ties, but the men's store retail spots only need a total of about, let's say, 8,000. They basically wasted material on making 2,000 ties, and so for that particular production cycle. And so you don't want to spend any money that you don't have to spend because they may eventually sell it. But the problem is if you're doing that every month, let's say for a whole year, then that 2,000 turns into 24,000 ties. And if you're not moving them or selling them, then you have to store them somewhere. And anytime you store something, you have to pay for that. And so that's money that the company is spending, meaning the subcontractor is spending on storing those ties, and they're not getting any money for it. So they want to make sure that they limit the maximum amount so that they don't have to incur those costs. Okay. All right. So down below, you see that we have information about the selling price per tie, as well as the minimum and maximum amount of demand. And of course, like I was saying before, the sub worries about this number, whereas the retailer is actually going to worry about this number. And of course, we're also given information about the total amount of material that it takes to make each tie. So this is like 1/8 of a yard here, and this is 8/100ths of a yard, and this is 1/10 of a yard. And so we see that's for the all silk tie, all polyester, and 50/50 cotton blend, and a 50/50 polyester cotton blend, and a 30/70 polyester cotton blend. And so, of course, this part is important because if we go back to the previous slide here, which I'll do that now, you see that we know how much we're paying per yard. Okay, so we can kind of guess how much each silk tie is going to cost based upon the cost, what it is per yard, and how much of that we're actually going to use. And that's important to us because we need to know the cost, because our profit is going to be revenue minus cost. Okay. So we have this information, and our goal here is to maximize the amount of money that we're going to make here. In other words, maximize our profits again. So moving on to the next slide here, it says the production process for all ties is almost fully automated, and Fifth Avenue uses a standard labor cost of 75 cents per tie, regardless of what type it is, okay? And we need to decide on a policy for the product mix in order to maximize its monthly profit. So again, our goal here is to maximize the monthly profit, and notice that we have the actual cost of making the ties involved, and that would come from both your labor cost that you see here as well as the material cost. So those are things that we have to consider. Now, the first thing that we want to do is set up what it is that we're looking for. In other words, define our variables. So we'll call S all silk ties, P all polyester, and then for the 50-50 blend, that'll be B1, and for the 30-70 poly cotton blend, that will be B2. And so now what we want to do is recall that whenever we were told that the profit that we're going to make on each table and chair here, for the Flair furniture example, we're going to be doing a similar thing for this example, but the difference now is we're going to be looking at unit profit versus just profit altogether, okay? And so again, how I mentioned, profit is revenue minus cost. So what we want to do is look at the all silk ties and kind of see how we put that together. So we know that the price per tie is going to be $6.70, okay? And of course, we get that from here, $6.70. We also know that it's going to cost us $20 a yard for silk. And of course, we're only using 1/8 of a yard per tie. So if we take the 1/8 of a yard, which is 0.125, and we multiply that times the 20 yards there, that's going to tell us pretty much how much is going to cost us to make one of those ties, okay? And in addition to that, we know that there is going to be an extra 75 cents charge per tie being made as well. So if we look at that, you see how we have the silk tie is going to be the price per tie minus the material cost minus the labor cost. And so again, and I'll go ahead and switch colors here so that we can kind of see what's going on. Move this out of the way. I'm going to go to black here for just a second. All right, so here we see that this $2.50 here, and this is per silk tie, should come from the 0.125 times 20. And it's basically 1/8. And of course, 20 and 8 both have a common factor of 4. So this would reduce to 1/2, and that would be 5, and that would be 5/2, which is 2.5. And that's how we get the $2.50 there. And of course, 75 cents we know comes from the labor cost. So that's how we're getting the profit, the unit profit for each silk tie. So we're saying $6.70 is the sale price, $2.50 is the material cost, plus another 75 cents to have the automation together to put together the ties. And so we see here that if we do that for the remaining ones, we'll have these particular equations here, okay? And I'll go back and I'll talk about each of these. Of course, the sale price, the $3.55, $4.31, and $4.81, if we go back, comes from here. $3.55, $4.31, $4.81. And of course, we see that for the polyester, that's the cheapest type of material here, so that's why the selling price is the least. And for the poly cotton blend, the 50/50, of course, that's going to be cheaper than if we use more cotton than polyester, because cotton is basically more expensive than polyester. And we see that from here. So you see the polyester is the cheapest material, which is $6. The cotton is more expensive than the polyester because it's priced at $9. Okay. So we see where the selling price comes from. Again, if we look at the cost per tie, we see that we have this is about 8/100ths of a yard for the all polyester. So if we take that and multiply that times 6 here, then we'll see what the total cost is for that. So the 0.08 times 6, and that would be 0.48 there. Get that to work. And let's see, yep, so that is cost of the polyester times the 0.08, and let me count, yeah, there we go. The 0.08 here is how many yards or what fraction of a yard we actually have here. And of course, for the poly cotton blend, this is going to be a little different, okay? So let's go back here first. So now you see where the cost comes from. Of course, for the polyester, you have 48 cents per polyester tie, and then the 75 cents for the labor charge, the automatic labor charge. Now for the blend 1 and the blend 2, this should actually be blend 2 here. So let's go ahead and fix that. For the blend 1 and the blend 2, what's different here is that, remember, we have 2 types of materials going on. So let's look at the blend 1 first. So if we look at the blend 1, we see we got a 50/50 polyester cotton blend. And so it takes a total of 1/10 of a yard to make this. So really what this is going to be split out in between is you got 5/100ths of a yard of polyester, and then you got 5/100ths of a yard of cotton. And so when we look at our costs for polyester and cotton, you're going to see here polyester costs $6, cotton costs $9. So if we take the 0.05 times the $6, that's going to tell us for the polyester part, plus 0.05 times the $9, that's going to be the cotton part. And of course, if we do that, 0.05 times 6 give us 0.3, plus 0.05 times 9 will give us 0.45, which will give us 0.75. And so that tells us for blend 1, the cost, the material cost per tie is going to be 75 cents. If we do the same thing with the blend 2, and I'll come up here and do that, for the blend 2, we know that there is a 30%, 70% blend for polyester and cotton. Okay, so For the polyester, it's 30%. Find somewhere else to do this because this doesn't look like it's going to work for me. So for the polyester, that's going to be 30%. And for the cotton, that's going to be 70%. So here we know that it cost $6 for the polyester. So again, we know that it takes about 1/10 of a yard for blend 2. So a 30-70 blend, 30% is just 0.03 of that. And we're going to multiply that times, for the polyester, to $6. Oops, move that back up. And then we're going to add on to that 0.07 times the cotton, which is $9. And then, of course, if we multiply the 0.03 times 6, we get 0.18. And multiply the 0.07 times 9, that's going to be 0.63. And of course, if we add that together, we're going to get 8 and 3 is 11. We carry the 1, and that's going to be 81 cents cost for blend 2. And so if we go back to what we see here, that should all kind of make sense here. So we see here we had 75 cents material cost for blend 1 and 81 cents material cost for blend 2. And of course, our labor cost is the same no matter what tie we're making. So that's how we come up with all of this. All right, and so now if we make unit profit, then we're taking we're going to take the price times the quantity for all 4 ties. So this is the all silk tie, this is the polyester tie, blend 1, blend 2, and then we're going to subtract from those profits that we get for all of those to be the material cost for the all silk tie, material cost for the polyester, material cost for the blend 1 and the blend 2. And then of course, we know that for each of these, the labor for automation of putting those ties together is 75 cents, and we subtract that as well. And so this ends up being our actual profit equation once we simplify all of this. And so now we're going to come up with our constraints and all of that. And when we come up with these constraints, we are going to get most of them from here, as well as from here. And of course, we know that we are limited to so much material. So we're going to have some material constraints for all 3 of the materials that we're using. And we're also going to have demand constraints. So we need to take all those things into account now. All right, so let's start with the constraints on the materials here. So for the silk ties, right? So we know we only have 1,000 yards for that, and the only time that we use silk is to make the all silk ties. Since we know it takes about 1/8 of a yard to be able to make 1 silk tie, then of course our constraint equation here would just be the 1/8 or the 0.125 times the number of silk ties that we make, and that's just going to have to be less than or equal to 1,000. So that's the only constraint that we have there. For the polyester, we have a total of 2,000 yards that we can use per month, but notice that the polyester is used for the all polyester tie as well as blend 1 and blend 2. And so for the all polyester tie, took us about 8/100ths of a yard, and we'll go back to that so that you can see it again. So here for the all polyester tie, we have 8/100ths of a yard. And we also know that for the poly cotton blend, for blend 1, we know that 50% of this 1/10 of a yard is going to be for polyester, okay? So we have to consider this. So the 0.05 of a yard that comes from the polyester part here, as well as the point, and I'll go ahead and put this down here too, the 0.03 portion, or the 3/100ths of a yard portion of the 30%, 70% poly cotton blend. So point in all that, when we see this, we know that here we have the 0.08 here for the polyester. Of course, that's how much it takes per yard to make that. For the 50/50 blend, 5/100ths of a yard is half of 1/10 of a yard. So we have this here. And then, of course, the 0.03 or the 3/100ths of a yard is 30% of 1/10 of a yard. And of course, all that times the number of all polyester blend 1 and blend 2 ties we make have to total out to be 2,000 yards. Similarly, for cotton, we know that we're using cotton in just blend 1 and blend 2, and we had a total of 1,250 yards for that. So again, for the blend 1, it's half and half. So since it took 1/10 of a yard to make blend 1, then 50% of that is 0.05 times blend 1. And for blend 2, we know is also 0.1, but for the cotton part, it was 70% of the 0.1 yard, or 1/10 of a yard, which is 7/100ths of a yard. And of course, these material amounts for each of those ties times the number of respective ties here have to be 1,250 yards or less per month. So that's how we get those particular constraints. If we keep on going, we see that for the all silk ties, we have to supply at least 6,000, no more than 7,000. And of course, that comes from, we'll go back here. So we want to do at least 6,000, no more than 7,000. For the all polyester, we want to make at least 10, no more than 14,000. For the poly cotton blend 1, at least 13,000, no more than 16,000. And for blend 2, at least 6,000, no more than 8,500. And so for here, this would just be kind of X's in between these two. So here, if I guess I need to put that in terms of S, not X, so it'll actually make sense. So if I did it that way, then it would look something like this, which means that S would have to be greater than or equal to 6,000, and in addition to that, S would have to be less than or equal to 7,000. So that's how and that's why you see those constraints written that way. So that's why you see it written separately like that. And of course, for the polyester, 10,000, 4,000. For the blend 1 and the blend 2, we see those respectively. All right, so we see how we come up with these constraints now. So if we look at everything together, we see that this is the list of inequality constraints that we have. And of course, the only other thing that we need to make sure of is that all of our variables, our silk ties, polyester ties, and the two blends, all of these are greater than or equal to 0, because we're not going to be producing negative numbers of ties. And so if we set up this problem by modeling it, this is one way that it could look when you put it into your Excel solver. So we see the formulas here. I'll actually show this on my in Excel so that you can actually see it. But main thing here I want to make sure that we get is that these yellow cells here are our decision variable cells. And you see that we have the selling price, the labor cost, and material cost. So we're compiling all that so that we can come up with a unit profit for each tie. And then after that, we're going to add all these up to come up with our profit. And then just like how we had in the last example, we used the sum product function in Excel to pretty much write all of our constraints here. And notice that all of these are intricately labeled so that we know exactly what we're talking about. And you also see that all the constraints that had less than or equal to signs in it, we put those in a group, and then all the ones that have greater than or equal to, we put those in a group. And then all these numbers that you see here in column H, these are the numbers that come from our material constraints as well as our demand constraints. And so the tables that we had before that gave us all that information, we're using all that stuff for our right-hand side of our constraints. So what we want to do now is actually see how do we run all this in the Excel solver again. So I'll bring up that actual Excel file and kind of take you through the steps again of how we use the Excel solver to come up with our solution. All right, so we're now at this example, and we see how we've put all of our information in from our constraint inequalities as well as our objective function. Put all this information together here. And just to take the silk tie as the example, we know that our selling price was $6.70. Our automated labor cost was 75 cents per silk tie. And we found out that our unit profit, sorry, not unit profit, but our material cost is $2.50 from that. And of course, if you remember, that actually came from the fact that we knew that it took about 1/8 of a yard to make that silk tie, which is about 0.125 or 125 1,000ths. And we multiply that times the 20 yards that we had, the $20 per yard that we knew it cost us for the silk. And that's how we got the 2.5. And then of course we do that for the polyester and the blend 1 and the blend 2. We see that we're getting our unit profit here for each type. And so now this is just a matter of taking the unit profit times the number of silk ties, unit profit for all polyester ties times the number of those, and respectively for blend 1 and blend 2. So how we put this into the Excel solver, again, we go to data. So you all will mostly be in home when you start off. Go to data, and under analysis, you'll click on the solver. And so now we'll go through this process again. So we want to set our objective function, which in this case is F9 right here. We want to maximize the profits again. So come and click on this cell, click on F9, and then click on this icon, and now we have it in. We want to change all of the cells that are in yellow because these are our decision variables. So we click on that, click and drag over all those cells, and then click on this icon. And we see we have them all in there. For our constraints, of course, we have many. We have our constraints that have less than or equal to signs, as well as those that have greater than or equal to signs. And we'll stop here at, I believe that is at row 17 for all the less than or equal to, and then we'll do 18 and down for the greater than or equal to. So we want to add our constraints, and remember we're going to do several of these at once here. So we'll click, and we're clicking on these blue cells and going all the way down until we get to row 17. So we're there, click. We know that we want less than or equal to, so we'll leave this the same, and then we'll come here to the constraints on the right hand side and click, go down until we get to row 17. And then we just click OK. So we see we have both things from rows 11 to row 17. Then we'll do the same thing for all the constraints that are greater than or equal to. So we'll add again, then we'll come here. So where the greater than or equal to starts, and we'll go all the way down. And here we'll change this to greater than or equal to, click, and come all the way down. And let's see, got that to 22, but I actually don't need the 22 here, so I'm going to redo this and just do it to 21. So let's add again, and I'm going to go down to this one because we don't have anything for the last one. And we'll come one more time, go here. So now we have everything we need. Of course, this needs to be checked to make sure that all of our variables are non-negative, and this needs to remain to be simplex LP for basically linear programming. And at that point, we just click solve, and we just wait for it, and we see that we came up with a solution, or the system came up with a solution. And so these are our optimum solutions here. Okay. And so, of course, at this point, this is all that we really care about at the moment. We see that our maximum profit is $55,905, okay? And, of course, as we get deeper into studying how we look at these models, we'll see that we can print out those answer reports or sensitivity reports and ask questions about the particular model that we have. But again, all that we care about is being able to model it, put it into Excel, and solve for our optimal solutions at this point. So let's go back to the presentation. All right, so we're going to do two more examples here. So the first example that we're going to do is we're going to do something a little different here. And we're going to talk about gambling junkets. And so what a gambling junket is basically it's an organization that schedules you to have quote unquote business meetings, but they're really fun meetings, to put it nicely. And we say that for this particular organization where they are located, they're trying to promote these gambling junkets so they can go to the Bahamas and let their clients have fun or whatnot. And so we know that this club has budgeted up to $8,000 a week for local advertising. So that's what is said here. Let's make sure that and the money is to be allocated amongst 4 different promotional media. So in other words, we want some TV spots, we want some in the newspaper, and we want to do 2 types of radio advertisements, which we see here is going to be prime time, 30-second slots, as well as the 1-minute afternoons. And the table down here sort of gives us information about what we know about those different media and time slots. So we see here that for each type of medium that we use, we have a maximum amount of people that we can reach, or I guess this may be an average of the amount of people that we can reach, and we know what the cost is per those ads, and we have a maximum on the amount of ads we can run like that per week. And so all this information is going to help us form our constraints that we need for our model. And so let's go a little further into this. We know that Big Wind's contractual arrangements require that at least 5 radio spots be placed each week. Okay, so in addition to these constraints on the number of weeks we can run the ad, as well as the audience that we're going to reach, we know that here we know at least 5 radio spots will be placed each week. So we're looking here, we know that for the radio spots in between these two, we have to have at least 5. Okay. We also know that we don't want to spend any more than $1,800 on radio advertising. And of course, that makes sense because with the radio advertising, of course, it's the cheaper out of that, but we want to make sure that we hit some of these other media for people who don't necessarily listen to radio, because we want to make sure that we advertise to demographic where we can reach, well, different demographics, I should say it that way. All right, and so those are our constraints here. So the first thing we want to do is formulate our problem. So let's identify the objective, and then we want to figure out what our decision variables are going to be. So our objective here is going to be Big Wind's goal is to reach the largest possible high potential audience through the various media. Okay, so what we want to do is maximize our audience. So what that means is if we come here, we want, since we know that we have on average about these number of people that will be reached by this particular medium, we want to come up with an objective function that has these coefficients in it, or these numbers in it. So we see here that the objective function is going to be, it's going to look like this. And of course, here we see that we're defining our variables. So T is just going to represent the TV spots, N is going to represent the newspaper ads, and P will stand for primetime radio spots, A will stand for afternoon 1-minute slots. And so you see here our max audience is just going to be the number of people on average that we can reach through TV, plus the number of people we can reach on average through newspaper, plus the number of people we can reach on average through primetime spots, the number of people we can reach through the afternoon spots. And of course, we know that the max advertising budget amongst all 4 media is going to be $8,000. Okay, so however much we're spending, we're going to have to max it out at $8,000 here. So I'm going to switch colors here for a second. And so if we go back to our cost per ad, we know that for the TV spots, it's just going to be 800 times the number of TV spots, plus newspaper ads going to be 925 per spot, or per full page ad. And then for the prime time, 290 for the radio spot, which is 1 minute in the afternoon. We have this. So if we add all these up, then we know that the total that we can spend there is going to be $8,000. So here, that's why we have this particular constraint here. And of course, that has to be less than or equal to $8,000. All right, so at least 5 radio spots. So we know that we have the prime time spots plus the afternoon spots, and it has to be greater than or equal to 5, because we need the total of those to be 5 or more. We also know that we don't want to spend any more than $1,800 on radio. So we know that for the radio, if we go back to that, we know that the 290 is for the prime time, 380 is for the afternoon. So 290 and 380. So 290 for the prime time plus 380 for the afternoon. That has to be limited to 1,800. And then maximum ads per week, we have those constraints as well. So if we come back here, we know that for TV, no more than 12, newspaper, no more than 5, primetime radio spot, no more than 25, and afternoon slot, no more than 20. And so when looking at it that way, we see how we actually come up with all these constraints here. So of course, prime time and afternoon has to be greater than or equal to 5 as far as the amount goes. Here is our $1,800 budget on just the radio portion. And here we know that the number of television, newspaper, primetime radio spots, and afternoon radio spots have basically have a max amount that they can have. Of course, your minimums are still, all of these have to be greater than or equal to 0. So we don't want to forget that as well. So moving on here, we see that for our max audience, here's our objective function. Here are our constraints. And if we set this up, this is kind of what it would look like. So we got our column for our TV spots, newspaper ads, prime time radio spots, and afternoon radio spots. Remember that our goal here is to get the maximum audience as possible. So of course, we know that for the TV spots, newspaper ad, prime time radio spots, and afternoon radio spots, we have on average the amount of people that we'll reach. And we're just going to take our constraint inequalities and form them here. And of course, if we take all that information, this is what it ends up looking like. Okay. And so by now, you should be kind of familiar with how we actually put this all together. Of course, these numbers here come from the chart that we had. I'll just go back there just to make sure that we all remember that. So those numbers come from there, and they are part of our objective function, which is to get the max audience or maximum number of people reached as possible. And so now all we need to do is run the Excel solver and see how we actually get these solutions here. So of course, when we run it, this is what we will get. And I'll go ahead and pause this and bring up the Microsoft Excel again so that we can run this quickly. All right, so we have set up here in Excel. So we'll just go again from home to data, and then under analysis, solver, and then we'll just put in all this information here. So we'll start off by our objective function, which is going to be in F6. We want the most amount of people as possible. So we'll click here, click on that cell, click the icon. Of course, we want to maximize the audience, so we keep this at a max. We want to change all of the yellow cells here. So we're going to click here, click and drag, or click, hold, and drag. And then we see that we have those cells captured. And now we're going to add our constraints. So again, all of these are less than or equal to inequality signs. So we're going to do all those constraints together. So we'll come here, drag all the way down to row 13. Click on this icon to store it. Leave that as less than or equal to. And then we'll come and do the same thing on the right hand side. From 12 down to $1,800. Click on that. Have OK. So now we'll add one more because we need to include the minimum radio spots here. And this needs to now be greater than or equal to. Come here, do 5, do that, OK. So now make sure that make unconstrained variables non-negative is checked to make sure that these values end up being non-negative values, and keep this in simplex LP. Solve, and we should get a solution, and we're done at that point. So one of the things that you see here is that, of course, these we'll have to round these numbers to actually make it make sense. So here we would say, all right, well, let's just use 2 TV spots, and let's use 6 primetime radio spots. And of course, the afternoon radio spots, we see that in order to maximize the number of people that we want to get, that we really don't need to run any during the afternoon radio spots at all. So that particular demographic, we're just not going to service them because we can maximize the amount of people that we get by doing the other 3. And so, of course, if we were willing to up our budget on the maximum amount of money that we would want to spend on the radio ads, we would probably be able to do more. But since we're trying to limit that, then that sort of takes out the afternoon radio spots here. And so now you see how this is ran in Excel. All right, so for our last example, what we're going to do is look at a situation where we have to consider the units changing. And so this example, we have a contestant on a hit reality show called Top Bartender, and they're asked to mix a variety of drinks, each consisting of 4 fluid ounces. So we know that all the drinks have to be 4 fluid ounces, and that's actually going to play a role in how we actually look at this. Other than the ingredients that you see below here, there are no other things permitted. And so we know that we have this total supply. So we have 128 ounces of bourbon, brandy, and vodka, and we have 32 ounces of dry and sweet vermouth. And of course, these will probably be more expensive than the vodka, brandy, and bourbon, so that's why we have less of it. So the contestant is considering making the following 4 drinks. So wants to make a New Yorker, which is 25% bourbon, brandy, vodka, and sweet vermouth. Okay. Now remember that each drink has to be 4 ounces. So 25% of 4 ounces is just 1 ounce, because 0.25 of 4 is just like 1/4 times 4, which is just 1. So here what we know is that we have 1 ounce of bourbon, 1 ounce of brandy, 1 ounce of vodka, and 1 ounce of sweet vermouth. For the Garibaldi, we know that we have 25% of each brandy and dry vermouth. So 1 ounce here, 1 ounce here, and we have 2 ounces of the sweet vermouth. Of course, for the Kentuckian, it's just 100% bourbon, so that's going to be 4 ounces. And the Russian, we see that we have 75% vodka and 25% sweet vermouth. So we know 25% of 4 ounces is 1 ounce, so that means 75% must be the other 3 for the vodka. And so the contestant's objective is to make the largest number of drinks with the available liquor. And we want to know what is the combination of drinks to meet this objective. All right, so the first thing that we need to do is define our variables. And so we'll have N, G, K, and R representing the number of New Yorkers, Garibaldis, Kentuckians, and Russians made. Okay. The next thing is our goal is to make the maximum number of drinks possible. So we basically just want to add up the numbers that we get from our decision variables. And so our constraints, we know that each drink can only be 4 ounces. So we actually kind of took care of that in terms of ounce-wise, how much everything is going to be sort of allocated for each drink. We know that we have limited quantities of bourbon, brandy, vodka, and sweet vermouth. Okay, and we're going to take that into account here. And each drink has different portions of the liquor. So we've kind of already taken care of this and this. We do need to pay a little bit more attention to this. So let's identify our constraints here. So we've already taken care of this part here as far as identifying how many ounces of what is going to be in the drinks. So this particular slide here takes care of that. And so now the part that we want to talk about here is the actual constraints on the amount of liquor that we have. So we know that for the New Yorker, it uses bourbon, and we know that Kentuckian uses bourbon. So now we're looking at what is bourbon used in, brandy, vodka, and sweet and dry vermouth, and making sure that we don't go over the amount that, or at least mathematically speaking, go over the amount that we have available to us. So here we know that the New Yorker uses 1 ounce of bourbon, and we know that 4 ounces of bourbon is used in the Kentuckian. So we got 1 ounce per New Yorker plus 4 ounces per Kentuckian, and that has to be less than or equal to 128 ounces. So for the brandy, we know that's used in New Yorker again and the Garibaldi. So really this could just be written as N plus G, which is the number of New Yorkers plus the number of Garibaldis, have to end up being 128 ounces as well. For vodka, we know that 1 ounce of vodka is used in the New Yorker and 3 ounces in the Russian. So this could just be N plus 3R is less than or equal to 128. And so again here, we're just looking at what drinks are actually, what particular type of liquor is used in what drinks. And we're just making sure that we don't go over the ounce limitations that we have. And then, of course, for the sweet vermouth, we know that the New Yorker uses 1 ounce of that, and it's 2 ounces in the Garibaldi. And of course, for the sweet and dry Vermouth, we only had 32 ounces, so this should be just 32 there. So number of New Yorkers plus 2 ounces per Garibaldi ends up being 32 ounces or less. And we have 1 ounce for the dry Vermouth for the Garibaldi and 1 ounce in the Russian. So looking at that, this is just Garibaldis plus number of Russians, and that has to be 32 ounces. And so when we look at all of that, this is what our constraints look like. Of course, noting that we can't make negative drinks. And then finally, if we set this up, then you'll see this is one way that it can be set up. We put in our coefficients here for our constraints. And of course, we see here for our objective function cell, we're trying to maximize the number of drinks. So we just add all of these numbers that we're getting ourselves together. And you see the sum product functions here. We just fill in everything. And whenever we run the Excel solver, just like how we did for the other 3 examples, we'll see that this is what we get for that. And of course, I won't run it this time because I think you pretty much got the handle on it, but you should get these answers here. And one thing that we notice is that in order for us to make the maximum amount of drinks as possible, we have to leave out making Garibaldis so we can get make the largest quantity of drinks that we can. Okay, and so this will conclude the presentation on linear programming modeling, and in particular using the Excel solver to help us out here. I hope this video helped. If it did, please let me know about it. And if you need to see anything else, just please feel free to contact me. If you're watching this on YouTube, you can send me a message through my YouTube page, or if you're actually in my course where I teach this, you can just contact me via email. And thank you so much for taking the time to watch this. I know it was long, but I hope it was informative. Take care.